Welcome to today's webinar. The webinar is organized by the Australian Stainless Steel Development Association, in short ASSDA, and conducted by the International Molybdenum Association, the Nickel Institute, and the Steel Construction Institute. It covers the topic of structural design of stainless steel. Today's presenter is Ms. Nancy Baddoo, Associate Director of the Steel Construction Institute. Our panelists today are Ms. Liesl Pilger, General Manager of ASSDA, and Dr. Graham Sussex, Technical Specialist of ASSDA. I'm your host today, Jörg Schweitzer, Manager Market Development in Southeast Asia. With this, I would like to wish you all a very interesting webinar. Over to you, Nancy.
Hello, good morning, good afternoon, everyone. Thank you for joining this webinar. Let me first explain what the Steel Construction Institute does. We are an organisation based in the UK, close to Heathrow Airport, and we promote the best use of steel in construction, whether that's steel in bridges, or modular construction, light gauge steel, offshore platforms, whether it's high strength steel or stainless steel. And my particular focus, I'm one of the structural engineers working at SCI. My particular focus is these high performance steels. So we write design standards, design guidance, software. We run advisory service, and we carry out independent assessment of products also. So this is how I propose to organize the webinar today. I'm going to divide it into 5 parts, and starting off right at the beginning, let me explain a few things about stainless steel. It's the name given to a family of corrosion and heat resisting alloys of steel. There's a wide range of stainless steels, and each with different levels of strength and corrosion resistance. But what makes it stainless is when the chromium content exceeds 10.5%, and you've got less carbon than 1.2%. Then it is a stainless steel, and a transparent and tightly adherent layer of chromium-rich oxide forms spontaneously on the surface of the steel. You can't see it. It's very, very thin, but it successfully prevents corrosion. Now, there are lots of different stainless steel alloys. Many have been custom made for different environmental conditions, but only a few are used in construction. Stainless steels are grouped into these families I show here, and the families have different microstructure and mechanical and physical properties, corrosion performance in different surface environments. And each of these families has different alloying element combinations. Chromium, molybdenum, and nitrogen, they're the primary alloying additions for increased corrosion resistance. And you need the nickel for improved formability and weldability. The austenitic stainless steels, they are ductile and reasonably strong. They can be readily formed and welded. Your kitchen sinks will probably be austenitic stainless steel, and higher strengths can be obtained by cold working. The duplex family of stainless steels have a mixed austenitic and ferritic microstructure. Now, they're not called duplex because there's a sort of a coated layer, which I know is the terminology used sometimes in the States. They're called duplex because it's a mixed microstructure. So they're through and through stainless steel. And they're a very useful family for structural applications because they're very strong, stronger than austenitics, and not quite as ductile. The ferritic family of stainless steels, they are slightly less strong and ductile than the austenitic steels. They tend to be used more in thin gauge application, and their corrosion resistance is generally inferior to the austenitics. And then the precipitation hardening stainless steels, they are very high strength. They tend to be used for high duty engineering components, sometimes for fasteners, but usually in aeronautical and space industries. And then finishing up with the martensitic stainless steels, they are less corrosion resistant than the austenitics. They're hardened by heat treatment, and they are the stainless steels that your kitchen knives tend to be made from. So for today's webinar, I'm going to focus on these two families of stainless steel. Most applications in architecture, building and construction will be using austenitic stainless steels. They have a wide range of corrosion resistance. They can be strengthened by cold working. It's interesting, but they're non-magnetic. You wouldn't necessarily expect that, but they are generally non-magnetic. They get a bit magnetic if they're cold worked. And we'll also cover the duplex stainless steels as we see them increasingly used for load-bearing applications where you can exploit the benefit of the higher strength. Also, they're more resistant to chloride stress corrosion cracking and crevice corrosion than austenitics, and they are magnetic. So while we're in the introduction, I want to talk through some of the drivers for using stainless steel in structures. The first, most obvious reason is because of their excellent corrosion resistance without needing an applied coating. So what applications, what industries do you think would benefit from this? Well, examples are the food and drink industry and the chemicals industry. Here it's of great benefit not to have an applied coating, which may need restoring or may fail and contaminate, say, the food and drink. The second reason is structures where you need a long design life and maintenance is difficult or impossible. What structures come to mind? Well, bridges is one example, and nuclear structures, again, maintenance is very difficult there. The third driver is where you can benefit from the wide choice of exposed metallic finishes. And here, of course, this is typically why stainless steel might be used for landmark structures, perhaps pedestrian bridges, sculptures, and also in the water, food, and drink industry. The fourth reason is because of the high resilience of stainless steel. I'm going to show you some of the mechanical properties of stainless steel. So you'll realize that it's a very useful metal for structures like blast resistance, perhaps blast walls on offshore platforms, for lock gates and barriers. The fifth driver for using stainless steel is that the austenitic family have an extraordinarily good toughness at very low temperatures. So they are used in cryogenic applications such as LNG tanks and in the chemicals industry. And as I mentioned, austenitics are non-magnetic, so that is used sometimes for certain structures in the medical or defense industries. Now I'm going to take you around the world, and we're going to look at some of these applications of load-bearing stainless steel, starting with buildings and external structures such as the Gap in Western Australia, where duplex stainless steel is used for this viewing platform, clearly used because good corrosion resistance is needed in this coastal location. But look at the photo below that. That's not quite so clear. Why would duplex stainless steel be chosen for the columns for the entrance structure at the 7 World Trade Center? Well, here, the columns needed to have very good impact resistance to withstand the possibility of vehicular impact. So duplex stainless steel was chosen. And then the photo on the right-hand side, that's a beautiful architectural canopy in London. Stainless steel here chosen for the aesthetic appearance. This is a very common application of stainless steel from rather straightforward glass steel structures, as I've shown here in Tottenham Court Road, the entrance to the underground there. But a more interesting subway entrance I'm showing on the right is South Ferry subway station in New York. Now, this subway was flooded during Hurricane Sandy a few years ago, and a lot of damage was done. Floodwaters rushed down, and all the mechanical and electrical equipment was spoilt by the floodwaters, and it was very, very costly to repair. So when they did redesign the subway entrance, they decided to redesign it like an inverted goldfish bowl, so that when floods were predicted, the entrance to the subway could shut and it would be completely dry inside and the waters outside. And so duplex stainless steel was needed here for its strength and resilience to withstand the flood loading. And just a different type of entrance canopy. Again, in the States, there are 42 now of these canopies to the Washington, D.C. Metro. And I'm showing you this one because this is a modular design. So the structures are fabricated off-site and the modules are bolted together on-site. So it's an austenitic stainless steel. But it's the speed of installation which was really so important for this structure. And it's clearly been a successful concept because it's been used 42 times. You'll be familiar with stainless steel being used for cladding and sculpture. I mean, the environmental conditions in Dubai can be quite extreme, strong winds, sandstorms, and stainless steel is an excellent material to withstand these weather conditions. Perhaps, though, the greatest application of load-bearing stainless steel is in these industrial structures. So, what am I showing here? The top left photo is a recently built modern biopharmaceutical production plant in Europe, and stainless steel is used for the platforms and the towers where you need to maintain and inspect the vessels. These would all be welded hollow sections. You don't have bolted connections because all the surfaces have to be readily cleaned. And then other industries, I won't go through them in detail: oil and gas, water, wastewater, desalination, lock gates. and of course the nuclear power plant, where stainless steel is used in a composite form of construction, where you have a plate of stainless, then concrete, and then a plate of carbon steel. You have the stainless where you need it for the corrosion resistance. Stainless steel bridges, well, you've probably seen pedestrian bridges made of stainless steel, but there is growing interest in the use of stainless steel even for road bridges, where the long life can justify the higher initial construction costs because you don't need to carry out expensive repainting. So in the UK, I just show the bottom left photo, that is Pooley Bridge. That's our new stainless steel road bridge in the Lake District. And in Australia, there's a very interesting stainless steel bridge in Sydney, where you use duplex plates for the primary deck structure, as well as duplex for the compression struts. And then you have a high nickel alloy for the pins and austenitic stainless steel for the balustrades. So it's a great example of the use of stainless steel in different components. And then finally, stainless steels are used for a wide range of applications in tunnels. For example, linings and their support framing, for cable trays, maintenance walkways, fixings, fasteners, lighting, signage, support, ground support anchors. And this tunnel in Brisbane, duplex stainless steel was used here for the stainless steel ties supporting the lining. I hope that's given you a little bit of a flavour of the different structural applications of stainless steel. They can be large or small, shiny or dull mill finish, quite a range. And now I'm going to talk through the properties that structural engineers will need in order to carry out design. On this graph, I'm comparing the stress strain characteristics of carbon steel, so that's in red, with stainless steel. And austenitic is in green and duplex in blue. So what strikes you when you see this? Carbon steel has the sharply defined yield point, with then followed by a plastic yield plateau. We all know that. Stainless steel, though, has this gradual yielding behavior with high strain hardening. By strain hardening, I mean the same as work hardening or cold working. We tend to use these terms interchangeably. But what I mean is that the strength increases with the plastic deformation. So, although the necessary steps to determine the structural capacity of stainless steel members and connections are very similar to the steps you use for carbon steel, these non-linear stress strain characteristics, they do impact some aspects of structural behavior. For example, local and global buckling response. More of that a bit later. At this stage, I'm just going to answer the question, what do you use for the yield strength when you don't have a sharply defined yield point like for carbon steel? And the convention is for materials like stainless steel and aluminium, high strength steels that behave like this, the convention is to use the strength at the 0.2% offset permanent strain, which I've shown in faint dotted lines on the graph. And this is the strength that will be given in the product standards. Now I'm going to show you the full range stress strain curves, taking us right up to fracture. And this enables us to compare the ductility and the energy absorption of stainless steel and carbon steel. What will strike you is that the austenitic stainless steel, so they're in green, are considerably more ductile than carbon steel. You can't always sort of benefit from this very high ductility, and indeed in some cases it's not helpful, but in some places you can. The energy absorption is the area under the stress strain curve. So you can see for austenitic stainless steel, it has much greater energy absorption due to the ductility and the strain hardening. Now I've got two tables to show you. So this first table is the mechanical properties that are given in the product standard. And starting with the yield strength, you can see that the austenitic stainless steels, their yield strength is lower than carbon steel, S355. The duplex steels, however, the strength is higher. It's 460 megapascals. The ratio between the tensile to the yield strength shows you the extent of the cold working, strain hardening. And you can see for the austenitic, the ratio is nearly 2.4. And the initial modulus is more or less the same stainless steel and carbon steel. Now, these strengths, these yield strengths, are properties in the annealed condition, which is a softened condition. You won't get any lower than that. When the material has been cold formed, for instance, then the strengths will increase. Let's look now at the physical properties. And it won't surprise you that they are going to be different from carbon steel because of the different chemical composition. So the coefficient of thermal expansion for austenitics is about 30% higher than that for carbon steel. So where you have carbon steel and austenitic stainless steel used together, the effects of differential thermal expansion should be considered in design. The thermal conductivity of both austenitic and duplex stainless steel is only about 30% that of carbon steel. So that can be useful and can be less useful. So sometimes you want low thermal conductivity if you're preventing the transfer of heat to enhance the energy efficiency. For example, when you're connecting a balcony, you might use a thermal break. So low thermal conductivity is helpful. But it can be less helpful, for example, when you're welding, because the heat doesn't get conducted away. Now, the final slide on the properties is showing the low temperature toughness. And the different families of stainless steel behave differently in this respect. The austenitic stainless steels really don't have a ductile to brittle transition. Very slightly reduces at very cold temperatures. The duplexes, they do have a ductile to brittle transition, rather like carbon steels. You don't buy the duplexes in the different qualities like you do for carbon steel, but there has been work to understand the maximum thicknesses that you can use the different duplex alloys at and have a comfortable margin against brittle failure. So that sort of guidance is going to go into the next version of the Eurocode. But generally, duplex stainless steels will be at least as good as carbon steels in terms of low temperature toughness. We're going to move on now to specification of stainless steel alloys. And I'm going to start by talking about how we call the different alloys. So in Australia, I understand that generally you use the American system of naming stainless steels, the ASSI system. So for the austenitics, you'd use the terminology 304, 304L, 316, 316L for the common austenitics. And for the duplexes, you'd use the terminology 2205 for the standard duplex. I've just put in grey the UNS system because that also can be used, and that is sort of a more official numbering system, and both the duplexes and the austenitics have a UNS number. In Europe, we have a different system, and this comprises a 1 dot and then a 4 and then 3 other digits. And there is also another system that can be used in Europe, but this tends to be the most common system. And in the Australian code 4673 cold formed stainless steel structures, you use the AISI numbering system. And I've put here on the slide the alloys that you cover in the standard. So the standard austenitics, and then the molybdenum austenitics, the duplex, and 2 ferritics. And you'll see that for one of the ferritics, you are actually using the European numbering system. So that is why I've shown on this slide the 2 designation systems. So now's the time to introduce you to these alloys in a little more detail. So the first thing I want to say is that when we say the word stainless steel grade or type, we actually mean the alloy, i.e. the composition, not the strength. So let's look at the left-hand side of this table. The standard chromium nickel austenitic alloys, 304 and 304L, they're the most common. They would be very widely used for applications like wind post and masonry support angles, for canopies, and they're suitable for rural and light urban environments. Then if you have a more corrosive environment, like an industrial or coastal environment, then you would want to use a more highly alloyed austenitic, and you would move to the 316 or 316L alloys, chromium, nickel, and molybdenum. Now, both these alloys are available in a wide range of product forms, and I want to explain this L. L stands for low carbon, and these days, generally these dual certification, these alloys are available as 304/304L, which provides the material with the slightly higher strength of 304 and the lower carbon content of 304L. What about the duplex alloys? Well, I'm just going to talk about the lean duplexes and the standard duplex. So the lean duplexes is lean in terms of the composition, chemical composition. This is a relatively new group of duplex stainless steels. They have a corrosion resistance between 304 and 316. And they're a really good choice for applications where you can benefit from the higher strength. The standard duplex, typically 2205, this is the most common duplex grade. It's been used for many decades in chemicals process industry and is being used more and more in structural applications. It's a highly alloyed chromium, nickel, molybdenum, nitrogen alloy, and it's suitable for severely corrosive environments, heavy industrial, coastal, or if you've got heavy de-icing salts. And it's available in a reasonably wide range of product forms. How do I know which alloy to choose? I've put on this slide some of the considerations which you would need to go through, of which the most important is the service environment. For example, what is the chloride salt deposition level? Is there exposure to de-icing salts? And if so, what type of chloride salts are used? Is the environment polluted? What is the frequency and quantity of expected rain? Is the structure going to be sheltered from rain? Rain washing is good, by the way. That's good. It washes off contaminants. So you want it to be exposed to rain. If it's very sheltered, then contaminants can build up. So service environment, both the macro and the micro scale, are really important. But there are these other issues you'd also want to think through, like strength and the details, how the structure will be fabricated, what finish is required. It's easier to get certain finishes on duplex, on austenitic rather than duplex, etc., etc. And the good news is there's lots of advice on alloy selection for structural applications. One source of advice is in the Eurocode 3 part 1.4. There's an annex giving you a step-by-step procedure. Another source of information is in the American Institute of Steel Construction specification and design guide. And if it's a more architectural application, I recommend you look at the site and design evaluation system on the IMOA website. Unlike carbon steel, there's generally no standard family of structural shapes for stainless steel. Although there is increasing availability of stainless steel hot rolled and laser welded open sections in the same sizes as you get for carbon steel. Generally, you get a wide range of shapes and section sizes available in the austenitic stainless steels. Custom fabrications and short runs are readily available in duplexes. Bear in mind, for stainless steel, you're more likely to use fabricated, optimized, custom design sections. And it's worth it because the material is more expensive. So what are the product standards? Generally, if you're using ASTMs, you will need to use two standards to specify a product. One for the chemistry and mechanical properties, and the other for the tolerances, finish, and anything else. So I've put an example here of the standards, you would need to specify plate, sheet, or strip. And the next slide, here we go. These are the standards you'd need for hot rolled and extruded structural shapes and bar. And for hollow sections, whether it's round or rectangular, you would want to refer to ASTM A554. What about bolts? Well, depending if you're using ISO or ASTM, there's an ISO standard that covers austenitic and duplex bolts. And there are a few ASTM standards. It's a bit confusing, the situation with ASTMs and stainless bolts. And in fact, we are writing an AISC design guide on stainless steel bolts, which hopefully will make it easier for specifiers to understand how to specify these bolts. That will be published next year. There are matching standards for nuts, no ASTM standards for washers, but there's a way around it. You specify the chemistry and mechanical requirements of the raw material and choose the alloy to match the bolts and nuts. If you're in the world of ISOs, then you may have come across bolts designated A470, for instance. A for austenitic, 4 is for the alloy, 4 is like a 316 alloy, and then the 70, 80 is the property class. So a bolt that's property class 80 has a tensile strength of 800 megapascals. So that's similar to a grade 8.8 carbon steel bolt. Now, for the remainder of our time, I am going to focus on design issues. Let's just look once again at those stress strain curves. And this is why you need special design rules in some instances for stainless steel, because of this non-linearity, which leads to differences in the resistance of members to buckling. So let's look at this in a bit more detail. So if you look at any of the elastic buckling resistance formula, you'll see that they have one thing in common. They're all proportional to E, the elastic modulus, whether it's local buckling of plates, column buckling, flexural torsional buckling, lateral torsional buckling, shear buckling, whatever. Now, the initial elastic modulus of stainless steel is similar to that of carbon steel. However, you can see in the figure, it decreases gradually before the material reaches its yield strength. And because of the reduction in modulus when the stress increases, the elastic buckling resistance also reduces. So if you wanted to calculate the elastic buckling load as a given stress level, you'd have to first calculate the tangent modulus at that particular stress level, and then use the tangent modulus to get the elastic buckling load. But that's such a pain. It would require iterations. So that's why in most stainless steel design codes, the buckling resistance is calculated using the initial elastic modulus, and the reduction of the modulus is accounted for by using different buckling coefficients from those that are used for carbon steel. There are other factors that also affect buckling behavior, such as geometric imperfections and residual stresses. Geometric imperfections are generally the same magnitude as for carbon steel. The imperfections at cross-section level affect local buckling, and they include outer plane imperfections of the flanges or the web. And at the member level, they include the outer straightness of a column. For example, that affects flexural buckling resistance. Now, it's the residual stresses of stainless steel which are generally different from those of carbon steel because they are dependent on the thermal properties. And you'll remember that I pointed out that thermal conductivity was rather low for stainless steel. Thermal expansion was greater. So this does tend to have an impact on the buckling resistance. And we'll see in this slide, not all the buckling modes are affected to the same degree by the non-linearity of the material characteristic or the residual stresses. For example, global buckling is known to be more affected than local buckling by these factors. So let's look at columns with low slenderness. That means short columns. The resistance is governed by yielding, and therefore the beneficial effect of strain hardening will result in a stainless steel column reaching a larger resistance than a carbon steel column. In a long column, or a column with high slenderness, the resistance is governed by global buckling, and in this case, the compressive stresses in the column will be below the limit of proportionality of stainless steel, and the behavior will be predominantly elastic. So stainless will behave the same way as a carbon steel column. But for columns of intermediate slenderness, the resistance is also governed by global buckling. But in this case, the compressive stresses in the column will be between the limit of proportionality and the yield strengths. And if you have a look at the figure, you can see this is the region where the detrimental effect of the non-linearity is more pronounced. So for the range of slenderness, for this range of slenderness, a stainless column can be expected to be less strong than a carbon steel column. So the gradual loss of stiffness exhibited by stainless steel before the yield strength, it implies that a stainless steel member will deflect more than an equivalent carbon steel member. It's not by a huge amount, but it should be taken into account. Most design codes recommend calculating the deflection of stainless steel members using the same traditional elastic equations that you use for carbon steel. But instead of using the elastic modulus, you use a secant modulus, a reduced modulus. And this reduced modulus is an average for the secant modulus in the compression and tension flange of the cross-section. So how do you calculate that secant modulus? Well, it's derived from the Ramberg-Osgood model, which is the classic model used to account for the gradual loss of stiffness for the material. And so if we have a simply supported beam subjected to uniformly distributed load, the maximum deflection, which takes place at midspan, can be calculated based on this reduced modulus of elasticity using the traditional elastic equation shown at the bottom of this slide. Now, this method is okay. It gives adequate predictions when the maximum stress in the cross-section is below 65% of the yield stress. When it gets for higher stresses, then the method becomes very conservative. The worst case is that for austenitics, you could possibly get up to, I think it's between 12 and 15% greater deflections. And for duplexes, it's maybe 5% greater deflections. So what are these design standards I've mentioned? Well, first of all, the Australian standard 4673 was published in 2000. The latest version is 2001. That it was based on the American standard ASCE 8 the version 1990, but the Australian standard was expanded in 2001 to cover a wider scope. It's now been withdrawn. I just wanted to point out that this is a standard for cold-formed stainless steel structures. So you wouldn't be using it to design heavier welded structures, for example, the bridge I showed you earlier on. And the other thing I wanted to say that despite its being withdrawn, specifiers can apparently still refer to it. And until something else becomes available, I guess it will be used, unless standards such as the American Institute of Steel Construction standard is preferred. Now, this is a pretty new American standard focusing on the design of bar plate and shapes. So it's not cold formed, covers austenitic and duplex stainless steels, and also includes precipitation hardening, alloys for tension members and fasteners. So it's based on the carbon steel standard AISC 360. Freely available for download at that link. And there's a AISC design guide, which gives lots more helpful information on alloy selection, design tables, and all those things. If you are interested in cold form stainless steel, then ASCE 8 was recently revised, and we were happy to play a part on that committee, as we were in preparing AISC 370 and the design guide. So this has had some significant revisions and brought it up to date in terms of alloys it covers and economic design methods. I just wanted to emphasize what I said, that ASCE 8 is for cold formed structures and AISC 370 is for bar and plate and welded structures. And they are quite different standards. 370 is sort of simpler to use, simpler solutions. ASCE 8, it sort of makes you work harder. It's more written for manufacturers in mind who want to get the last percent of capacity out of their products. And I also should mention that there is a Eurocode for structural stainless steel, Eurocode 3 part 1.4, which has a broad scope. It covers hot rolled, welded, cold formed, and bar. It underwent a significant amendment in 2015. There's been another amendment in 2020. It's a short standard because it's supplementary. It modifies and supplements the rules for carbon steel. So if the carbon steel rules apply, then that's fine, nothing's given. It's only where you need special stainless rules, you'll find them in this part of the Eurocode. Second generation Eurocodes are around the corner, and in fact the stainless Eurocode will be available come January. Second generation, it can't be used yet. We have to write a national annex before it can be used, so it'll still be a couple of years off before the second generation Eurocodes are properly used. And I would bring to your attention that there is a design manual for structural stainless steel, which is like a design guide for the Eurocode. It's like a one-stop shop giving design rules and information on structural stainless steel in accordance with the Eurocodes. So let me summarize a few things about design. Follow the same basic approach as carbon steel. Of course, it's a steel, so you would expect that. You must make sure that you use the correct resistance factors or safety factors for stainless steel, because they may be different. In the Eurocode world, they are different for stainless steel. You'd end up using the same rules for tension members and restrained beams, because non-linearity doesn't come into that behavior. But you would need to follow special rules for alloy selection, for buckling, section classification, structural analysis, deflection, and opportunities to exploit the benefits of strain hardening should be seriously considered if you're designing, for example, cold-formed hollow sections. Here's a table from AISC 370, just showing the difference you might expect for cross-section classification. So in red, I'm showing the limits for stainless steel, which are slightly lower than the limits for carbon steel. Here I am showing buckling curves for columns, and I'm just I'm showing a lot on this slide, and there isn't time to take you through all of it, but I've shown in black the carbon steel buckling curve, which is one buckling curve in AISC world. For stainless steel, we actually have introduced 3 buckling curves. It's, the material, you want to use it economically, so let's get some good buckling curves there, and you'll see that we have a plateau, a yield plateau at the start of the buckling curves for stainless steel when no reduction is necessary. And one other example of the different design approach is for stainless steel. You can take account of the strength enhancement due to cold forming, and for rectangular hollow sections, you get the largest increase in strength around the corners, but also the flat portions experience an increase in strength. And for circular hollow sections, it's an even increase all around. Greatest effect is for compact sections and for austenitic stainless steels, which show more non-linearity. Well, our time is up. I just had a couple of slides on connections before I finish. So a key point for connections is the corrosion resistance of a stainless fastener should be at least equivalent to the material being joined. So use a 316 alloy bolt if you're joining 316 material, and do not use galvanized bolts in stainless steel plate. Generally, the design rules are the same for bolted connections, some differences when it comes to bearing rules. I think in separate webinars, you've covered fabrication issues where you've talked about this phenomenon galling, which can occur when you have surfaces under load and in relative motion. And stainless steel, like some other metals, can be prone to galling. So you do need to take certain measures, and in particular, make sure you're using an appropriate lubrication. You're often joining stainless with other metals, and if it's in a wet or immersed environment, then there's a risk of bimetallic corrosion. And so it is preferable to exclude water from the joint or isolate the metals. And there are various approaches to isolation. I've shown one in these in this drawing. You would, I've mentioned already, you shouldn't use galvanized steel bolts in a stainless steel plate. Stainless steel bolts, however, in carbon steel is a better situation. You might want to isolate it still if it's in a very corrosive environment or if it's likely to be immersed in water for a long time. This phenomenon, bimetallic corrosion, is very difficult to predict. It depends on a number of issues, and I can't go into it, unfortunately, in any detail now, but it's well documented in the design guides. And then finally, welded connections. Stainless steel is weldable. With the duplex stainless steels, you need more control of the minimum and maximum heat input during welding. Distortion, I've mentioned, could be a problem because of these different thermal properties, high thermal expansion, low conductivity. So you do have to design the welded joints so that you can control distortion as far as possible. And very importantly, use suitable welding procedures, qualified welders, and compatible consumables. Can you weld stainless steel to carbon steel? Yes, it is often done. Make sure you use the right filler metal. And if you're in a very corrosive environment with moisture present, you would extend the painted coating that's already on your carbon steel over the weld and on the stainless steel for about 75 millimeters. This is good practice to avoid issues related to bimetallic corrosion. That was a bit of a whirlwind tour, but I hope that the takeaways of today's webinar are that stainless steel is a corrosion-resistant alloy suitable for aggressive environments or where maintenance is difficult, where you want a very long design life, and for architectural reasons. Different alloys suitable for different environments. And there are modern design standards for structural engineers covering stainless steel products, design and fabrication. So that's me finished. Thank you for listening.
Thank you, Nancy, for this very interesting presentation. Dear listeners, if you have any question concerning this presentation or about any nickel-related topic, kindly send us your question via our webpage. Once you enter www.nickelinstitute.org, you will immediately see the yellow banner Technical Help. Click on it, register, it's free of charge, and then fill in your question. One of our experts will come back to you fastest. Thank you all for attending this webinar. We are looking forward to have you on one of our next webinars again. Goodbye.